So welcome. This is the second part of my presentation on the statistical inference of multi-way network paper. Here I'm talking more about the package, the polyots package, and I want to display some simple usage case of the package. So first thing, in this demonstration, we need to install the package in case it's not installed yet. I'm using Google Colab so we can have some sort of environment that everyone can follow. And to install the package, you just hit pip install polyots and run. It will collect and install the package. So we see it's done. Now we can proceed to discuss how to use the method. First, I will need some data. I will construct here artificial data using the following DGP. So I will look at two-way data for simplicity. So I care here about patients and doctors. Each patient and doctor will live in a city. I will have here 100 possible cities, and I will put these cities in a 10 by 10 grid. The covariate xij, so xi doctor, j patient, will simply be the distance between patient I and Dr. J. The structural parameter beta in this example will be just a univariate vector with one entry -5. And the DGP, of course, will contain fixed effects, although it doesn't matter for the polyots method itself. So here I'm just constructing this data set. So the data set itself, what we need to the method, so let me run that. We will need one data frame, one pandas data frame in the long format, and this pandas data frame must look like this. So we have one column for each index. So if you have many coordinates, for instance, in a four-way, we need four columns here. In the two-way, we need only two. In the D-way, we need D columns, one for each coordinate. So here I have just a patient and doctor. So patient 1, doctor 19. And I will need another column to say which is the value of y, so the counter at this pair of patient and doctor. So in general, what I have here is I1 up to ID and Y I1 ID. Besides that, we only need to save here in the input, to have in this input the lines for which this the counter, which here is the variable visits, is bigger than 0. So all the other lines you can just discard. In this case, we have, in this example, we have just almost 700 non-zero edges. Out of, I have here 1,000 patients and 100 doctors. So out of 100,000 possible edges, since it's quite sparse, I have only 700 non-zero edges. So just to show, besides the data frame, we also have a tensor storing the covariates, so storing the features of the pairs in this case the distance, that I can access that way here. So for instance, if I take the patient ID 1 and the doctor ID 1, this is I should be able to access the distance through X, patient ID, doctor ID. This should be a tensor with d plus 1 dimensions, where the last dimension is just the number of features that you care about. In this case, it's just one feature. Beta has only one coordinate, one entry. But even though it's when I look here, what I get is a vector with one entry. It could be as many as we are interested in, as many structural parameters as we have. So just to see here, for instance, we know that at patient ID 1 and doctor ID 19, we have one visit. So let's see which is the distance between this patient and this doctor, and we see that we have a distance of 0, which makes sense, right? So we tend to, by the DGP, people would prefer to go to doctors that are close to them. So we can check again here, for instance, patient ID 3 and doctor ID 96, and again we have 0. Probably one of these examples here may not be at 0, but most of these examples will happen exactly at a 0. So alternatively, we also provide, if we can't provide X, we can provide in place of X all the information that is necessary to construct X. We will see that this is quite useful if you have a very, very large sparse network. So in this case, for instance, instead of providing this matrix, this tensor, which is of 1000 by 100 by 1, you can just provide the list of cities associated with each patient, the cities associated with each doctor, and some matrix of distance between all cities and between all cities in your map. So in this case, for instance, I have the city of patient 3 and the city of doctor 96. So it's the same city, it's the city number 42. And I also provide here the distance matrix between these cities. In this case, I will see the distance between city 42 and 42, which is of course 0, right? We could take, for instance, 3, 1. Here we have a distance of 2. In this case, it's city 42 and city 40, and of course, the distance is 2. Notice that here we needed to store a matrix of size 100,000, but here we stored this list of patient cities, which is of size 100, plus the list of doctor cities, which of size, of size 1000, plus doctor cities, which is of size 100, and also this matrix of city distances, which is 100 by 100. So in practice, here we needed 100,000 data points, and here we only needed, it's basically 11,100 data points. It's 10%, 11% to be more accurate, of the memory usage of this first example. And this is quite important when we are in a very large data set. So now let's see how to use the package. The package is structured to be easy to use to people who are familiar with scikit-learn, because we follow the same guidelines, but I will exemplify here. I will give the 2 possible usages. The first one is when we are capable of having the tensor of covariates in memory, so this tensor X here. And the other one is when we can't have X in memory, but we can evaluate some entries on demand. And this is quite interesting because if you have a very sparse and large data set, as I said, you don't need to evaluate all features to implement the polyads method, so you can let the library, the method, do it for you and select only the features that it will actually need to evaluate. So let's look at the the first usage case, which is the simplest one. So I go in the polyads library and I import the polyad estimator. Polyad estimator is a class. I will now instantiate an object, so the estimator is a polyad estimator. I have many configurations here. I will just set here to use TTDM so we can see a progress bar. Of course, you can learn more about these configurations in the documentation of the package, which is available on the GitHub. Just as in scikit, we can fit. So in order to fit, we need to provide the data frame. Then I need to provide a list of the columns of the data frame that contain the coordinates for each index. So in this case, it's a patient ID. Recall here in my data frame, I have patient ID and doctor ID. And it's in this exact order. Then doctor ID. Then I need to inform which is the free variable. In this case, it's visits. So Y is given by the column visits. Then I can provide some initial value for beta, just to start the optimization. I will give 0. And since I have the feature x, I provide x equals to x. And in the end here, I would just require a short summary of the results. So I hit run. We see here that it found that we have these many non-negative edges. It's gathering the polyads that use these pairs of edges. It found basically 200,000 polyads. It's now running the optimization. So we have here the results that we care about. The estimated coefficient was basically minus 4.9. The correct one in the DGP was minus 5. And we see that the 95 confidence interval goes from minus 5.5 to minus 4.3. So the correct guy is inside this confidence interval. I also provide here the standard error, the z statistic, and the probability of being bigger than z. Meanwhile, the other way of implementing is without providing the x, but providing the means to find to evaluate x on demand. So in this case, I need to construct some function that I will call in this case properly a get distance. This function must take as first index a vector given the index. Then it should take the features that I want to give for it. So for instance, I will need to compute the distance at coordinate IDX. IDX here stands for I1 up to ID, in this case IJ, patient doctor. I will need to do that. I will need the patient cities, the list of cities of patients, the doctor cities, and the city distance matrix. And as the autocomplete already did here, we just need to return the city distance matrix evaluated at the city of this patient, which patient, exactly this guy here, so I, and also the city of Dr. J, so ij is simply in this case that. So this is the function that we need. To call the estimator, we do more or less the same thing, but the fit will be slightly different. So here in the fit, we need again to provide the data frame, as always. We also need to provide the list of indices, also need to provide the y's, the column of the y's. We also provide some initial beta for the optimization. But now, instead of providing x equals to x, we provide eval x equals to get distance. So we pass the function to the fit. And we also provide here all the arguments that this function may need. So in this case, it will make use of patient cities. So I pass to the variable patient cities, I will pass the list of patient cities, and so on. And then this should be enough. I will also take the summary here, and let's see what happens. And we get basically the same results because it's just another way of calling the function. But we see here, so the same coefficient. You see here the same coefficient, the same confidence interval. We saw the same number of active edges, the same number of polyoids. So basically the same result. It's just another way of calling the function that works better in a larger data set. So to know details about how to use this package, I'd refer to the documentation and about how the package works, how the method works. I'd refer to the paper itself. Hope it was helpful, and that's all.